Hi, welcome back to Mrs. Thompson's classroom. Today we're going to talk about rational functions. This is part one of this video series. Today we're going to talk specifically about asymptotes. So we're going to talk first about how to find vertical asymptotes. So a vertical asymptote is an invisible vertical line that a function approaches but does not cross. And so when you're talking rational functions, the basic rational function 1 over x looks like this. It has a vertical asymptote at x equals 0. We don't see that line, but we can see that the graph is going up towards it on the right and down towards it on the left. So to locate them, we're going to reduce the fraction first, because rational functions all are fractions. We're going to reduce it first and then set the denominator equal to 0. Okay, so to do these first ones, again, we're going to take the denominator and factor. We notice that this function does not reduce, so then I take the denominator and I set it equal to 0. So that would tell me x minus 3 is 0, or x plus 3 is 0. So x equals 3 or negative 3 are my vertical asymptotes. Now, if you remember from the video on domain, that would mean that the domain is x not equal to 3 or negative 3, because the function will never touch that vertical line. Okay, in part B here, if I factor the denominator, okay, the minus 4 goes to minus 2 and plus 2. Now this is going to reduce. So now this tells me x equals 2 is the vertical asymptote. Okay. However, the domain of this function would be x not equal to 2, and this right here still tells me x cannot equal negative 2. Okay? Because it reduced, it is not a vertical asymptote, but it is not allowed in the domain. The function would still be undefined there. What we actually find is a hole. The graph has a hole. Okay, in this bottom function, x squared plus 4 doesn't factor, so this is not going to reduce. But if I set x squared plus 4 equal to 0, I'm going to get x squared equals negative 4. So x is going to be plus or minus the square root of negative 4, which is 2i. Because this is imaginary and not real, there are no vertical asymptotes, which means the domain would simply be all reals. Okay? All right, so that's vertical asymptotes. Rational functions can also have horizontal asymptotes. So a horizontal asymptote is going to be y equals, because it's a horizontal line. Again, if we look at that basic function, what I'm talking about with my horizontal asymptotes are what is the function doing as x goes to infinity. Okay, or as x goes to negative infinity on the left. This is the question. If I have a horizontal asymptote, then those two answers, those two question marks, will be real numbers. Okay? So we're going to let f be some rational function, p over q. And if the degree of the numerator is smaller, okay, then the horizontal asymptote is always at y equals 0, like in the picture I just drew. If the degrees are equal, then we're going to use their leading coefficients. Okay? And if the numerator's degree is bigger, then we don't have one. Okay, now that's a lot of words. So let's actually get down to some examples so I can explain what that means. Okay. All right. So in this first example, the degree of the numerator is 1, and the degree of the denominator is 2. Okay, so this means the degree of the numerator is smaller, so that my y asymptote would be at 0. But why? Let's see if we can take a look and figure out why. Okay, so let's take the entire function and divide out that largest exponent. So the largest exponent would be x squared. So I'm going to take the denominator and I'm going to divide by x squared. And I'm going to take the numerator and divide by x squared. If I do that on the top and the bottom, all I've done is multiply by 1, so I haven't changed anything. So this would get me 2 over x minus 1 over x squared over 1 minus 1 over x squared. Okay, now we know, as I drew that basic graph here a minute ago, 1 over x goes to y equals 0. This one is a known. This is one of our basic functions, okay, that we can kind of go to do all of our transformations and so forth. So each piece then can be dealt with individually. Well, this part's going to 0 because of this graph here. That means this one's going to 0 and this one's going to 0. So my answer is 0 over 1, which is 0, hence my answer. Now, in general, the largest exponent is the ruling factor in these problems. And so it is what we call the ocean. It is the big piece, and it is the one that's going to determine whether we have a horizontal asymptote or not, whether the function is approaching some number or whether it's just continuing to get bigger and bigger and bigger. Okay, so when the ocean is on the bottom, okay, that x squared is the ocean. Everything else is spit. Okay, this and this is all just spit. So as x gets huge, basically what this whole, as x goes to infinity, as x gets huge, becomes a million, a billion, a trillion, a quadrillion, as it gets huge, basically the spit over ocean becomes 1 over an infinity, which will tend towards 0. So if the largest exponent and the controlling piece is in the bottom, that's where the ocean is, then it's going to go to 0. So if you think about the ocean, that's a lot of water. If you just spit in the ocean, that's such a negligibly small amount of water that you just added. You didn't change the amount of water. And so the ocean is the controlling piece. So now let's look at this next one. Okay, here the degrees are the same. So this is an instance where we have ocean over ocean. Okay, so in this case, this is the spit. And what this tends towards, as x gets huge, this ends up as 2x squared over x squared. The controlling piece is all I'm concerned with. Well, that's going to reduce to 2. So my horizontal asymptote is at y equals 2. Okay, what we're actually doing here is some calculus. We're taking the limit as x goes to infinity of our function will equal 2. So if we want to describe the end behavior, so of this first one, as x goes to infinity, f of x goes to 0. So we can describe the end behavior as x goes to negative infinity, f of x goes to 0. Now, it is possible to have two different values here, but we kind of have to add in some maybe absolute values or different things to cause that to happen. So for the rational functions I'm dealing with right now, they're going to go to the same thing on both sides. Okay, and then here we'd have the limit as x goes to negative infinity will equal 2 as well. Okay, now let's take a look at this last one. Now our ocean is on the top. So this is ocean over spit. So all of this is spit. Okay, so as x goes to infinity, this function just actually goes to 2x cubed. That's the controlling factor. So as x goes to a positive infinity, this is going to infinity. So that means I have no horizontal asymptote. Okay, and I would describe the end behavior in this way. This means on my graph, the function's going to be going up. It's not going to be coming towards something like it does in this one. Now, as x goes to negative infinity, okay, if I put a negative infinity in here, then this is going to stay negative, and so it's going down this way. Remember, it's a cubic here, so I would go from down to up, okay? We learned that with our leading coefficient test for polynomials, okay? So that's how we find vertical and horizontal asymptotes. So you can take some practice at that, look at different functions. Next time we'll learn how to use that information to graph these functions. All right, so I will see you next time.